We're back, and we've got Ralph Showalter here from Oregon State. Ralph will be talking about multiscale systems for flow and transport.
Thank you. I want to thank the organizers for including me in this workshop. It's been a great pleasure. I'm still on the low and steep end of the learning curve for this subject. Most of it is, if not all of it, is new to me. And it's been a great pleasure to meet you. Today I'd like to share with you some work we had done a couple years back. Coming from groundwater flow, involved some multi-scale issues. Homogenization was a central part of the initial theme, and the objective was to build a model which could be numerically implemented to describe certain phenomena which we had seen in some what I thought of as startling experiments from some of our neighbors in groundwater flow. I've arranged my talk in the following way. 95% of it will be on the first two chapters, and some just passing comments on the last part, which is a direction which we were motivated to explore, and the consequence of the exploration was that we don't want to go down that road. So I will not dwell a lot on that, except point to show you what happened at the end, and then you can guess from what you see why we didn't want to go that way. Porous media flow through the ground. This is not an ice slab. We did not have to cut it out of the ground and lift it up with a derrick and take a picture of it. But in fact, you put a backhoe up against the wall and you dig out a hole and you take a picture of what happens when you take a dye-filled liquid like water and just pour it into the ground, and it goes seeping down below. And as you'll see, the inhomogeneities in the medium add a lot to the confused behavior of the flow downward. It's pretty much saturated up here, and as it went down, you can see these little rivers that go following the larger fissures that were there on their own. And in fact, it's quite pronounced. There are even some, you can spot a few of them down here, where some of it leached in and then came out toward the front. Lack of homogeneity is ubiquitous. Here's the mathematician's toy model of certain aspect of this process. Yes?
Just out of curiosity, can I ask, was the soil dry or wet when you poured the water on the top?
I didn't pour it, but it was probably dry. Yes. So it's really a two-phase situation, which I'm really not talking about today. What I do want to talk about, and then I'll relate this to some reality in a minute, but this idealized situation, this is a schematic in a porous medium, which has two values for the permeability associated with it. The blue islands are regions of low permeability. The red connected regions are much higher permeability regions. And so you can see that with a pressure difference across here, most of the liquid will flow through the red region rather quickly, and there'll be a smaller amounts going through the blue, which is sort of inherited from its neighbors. The exercise here is the following. Have a uniform, it's fully saturated. Suppose you have a uniform concentration of some chemical in the water, which is in there, and then from the left side you start injecting at a fixed rate a clear liquid, no concentration. And then you watch what happens at the other side, what comes out. That's sort of a standard exercise where you look at what comes out the other end, called the breakthrough curve, which gives you a signature of what was going on back in the porous media. Not the whole picture, but an important signal.
Ralph?
Yes.
So what sort of length scales are you thinking about here?
Okay. Two choices. In porous media, we have really three scales we think about. There's the pore scale, which is modeled at the level of Stokes' equation. Then there's a laboratory scale, which is upscaled from that, which where we first see the Darcy law. Okay? And then when we go into field scales, where we'll see, again, Darcy law, but with much more inhomogeneity because of different parameters.
But for this red-blue model,
This could be either 2 or 3.
okay.
This could be either lab scale. In fact, the experiments I have are exactly lab scale like this size, okay, something like a meter. But the same thing would be used as a model for kilometer scale, which our oil producers would use. Okay, oil retrievers would use. Okay, so the standard model is have a one-way coupled system of equations, Darcy's law, divergence free, okay, no sources. So this determines the flow. And the flow is determined, of course, by the permeability. Okay, once you determine the flow, that becomes a coefficient in your equation for an advection term. For C is the concentration, which is being transported by that flow. And there's a diffusion coefficient here, which can change with the velocity. So there's a function of the velocity there. So basically, once you solve this guy first for the velocity, then you use that as data down here to set up that equation, and you solve that one for the transport issues. Okay? Now, in our project, we carried along both of these. So at the very end, I'll say something about that system. One-way coupled, so it's really 2 separate problems, with one affecting the other. I'll tell you something about that system, the consequences for that system at the end, but in order to simplify things, and I'm really streamlining things quite a bit, so I want to just sort of focus in on the heart of the matter. I'm going to concentrate on just the parabolic equation, and if you prefer to think about the flow, you just ignore the time dependence. Okay, so if you just ignore that, you basically got a special case. You get the first one as a special case. But that's not the way we think of it. If you eliminate the d by dt term, you've got an elliptic problem you're looking at. Okay? But it's a time-dependent problem. It's the important one here. And by the way, when you go from the time-dependent to the corresponding stationary problem, parts of this model we're talking about actually just fall apart. They just don't make any sense anymore. Well, I'll mention that as we get into it. Okay, so we're going to be talking about a concentration transport. So I'm going to assume that the U is given to me, and then I'll concentrate on solving this parabolic equation here, describing the concentration which is being transported through this medium with 2 different permeabilities, a large one for the fast flow, a small one for the slow flow, okay? And these in turn affect these guys here. So I'm really looking at this part of the model right here. I'm looking at the concentration in the fast and slow regions. Okay. Classically, this was an important problem in the oil industry because in fact, in all of the applications, what happens is that these islands, these inclusions with very low permeability, tend to store the concentration there. It gets leaked out of those much, much more slowly than it does out of the fissured system. Everything starts off at a uniform concentration, but when you go to flush it, these little islands retain it on a different time scale. So there's a big time delay in what gets wiped out of those islands.
And are you imagining that the blue is the dominant volume share too?
Yes. In fact, in the extreme case, the blue takes up all the volume. That's all of the capacity, comparatively. And so all of the flow is in the red region, and all the storage is in the blue region, and they're coupled somehow. That's sort of the extreme case. Okay. What we call fissured medium.
Can I ask
Yes.
you one quick question? I'm just trying to figure out how does the diffusivity, physically speaking, how does the velocity makes the diffusivity change? If you increase the magnitude of the velocity, the diffusivity changes.
Because of
How does that
dispersion.
work?
Because
Okay,
of dispersion.
Sure.
Yeah.
Okay.
Right. If you faster, there's more action and there's more moving about.
Is that
More transverse versus.
an isotropic tensor, or
Yes. We'll get enough interest in it in that case. where each of the k's is in fact a constant. You can take them constant. Okay. All right. Wrong way. If I do a one-dimensional version of it, think of this flushing. I have a uniform concentration of 1. I put in a clear fluid from the other end. What happens is that first we see at the other end we're reading off the concentration, and suddenly we just run out of it and it's gone. Okay? That's an idealized case. There is some diffusion. It'll spread this guy out. It'll be spread out along like so. And if we have the interaction, I keep going backwards, and if I have interaction with the extra storage for those other terms, I'll have other effects coming in. This was coming from a different direction, so I don't want to dwell on it. But the point is that these different diffusion rates and the different storage rates really spread out this wave that we see coming out the end, and it affects the breakthrough curves.
Can we go back just to interpret the breakthrough curves?
Yes.
So this is where you're sitting at the source.
I put in this is all uniformly one color. Okay. I put in a clear fluid here, and it goes there and starts sweeping it out.
So
Okay. And I go in here and I measure concentration of what's coming out that end. So what you see on these graphs is a concentration coming across the end.
So why is it 1 at time 0?
Because it's 1 throughout the whole tube. Then I put in a concentration 0 at this end, and that 0 has to move up through here. And when it gets up to here, then that 0 drops down there.
Okay.
He started with a high concentration.
Yes.
And run the water to
Okay.
dilute it.
Okay. Oh, so this is it flushing out.
I'm
Yes.
flushing out the
Okay.
concentration that's already there.
Okay.
Right. Okay. This picture came from a chromatography simulation, which it's not quite the same thing, so there's some extra delays in here. Okay. Here is the experiment, and I'm going to look at pieces of this in more detail in a minute, but I just want to sort of give you the big picture. In that red-blue diagram I had, the important thing we want to study is the ratio of those two permeabilities. On the left side is a situation that comes up, and I'm going to go back and repeat this as I go through this. I'm going to sweep through these 3 successive pictures repeatedly. But on the left side, this is a low contrast case. Maybe the high one is 6 times bigger than the low one. The ratio of them is about in the order of around 10, 6 to 10, something like that. Not a big difference. And you can see here it's increasing with time as we go through here. The red is the concentration. We're flushing it out with the clear, which is blue. And there's intermediate green there. And so basically the clear liquid's coming in, and there's a lot of motion around the little particles. Inside here were lots of little circular particles that were manufactured and inserted in this experiment. This is experimental. And I'll describe that again in a minute when I show you more of it. But you can see the liquid coming in from the right and sweeping through here. And it doesn't look too non-homogeneous at this point, because those islands are the same order of magnitude as the surrounding region. There was some mixing because these islands are a little bit different. But aside from a little bit of extra mixing, more than you would expect here, and these little fingers here are caused in part by these inclusions. But you can see a not too far from uniform wavefront coming through here. So you'd be reading a 1 here for a while, then along here you'd sweep real quickly from here to here. You'd sweep up from 1 down to 0 in your breakthrough curve that you saw.
So okay. The islands is
Okay.
considered.
You can't see them here yet,
I see.
but they are there. Now, let's change the contrast. I'm going to change the contrast from about 6 or 10 up to about 100. That's a scale change. Now you see something different. Now you can actually see the islands. This is starting at time 0 and moving up here, and then I switch up to this one because I wanted to track it for longer. Because of the extra delays, I have to wait longer to see what's happening. And that's why I needed 2 columns to represent this. Well, the experimenters needed 2 columns to represent this. And these are the people who did this experiment. And that tells you about the time we started, because we found it. We started after we saw these. You see the little islands here. Now what they have here is a planar flow field they've constructed, all right? And inside that permeability field, which was made out of glass particles, they made lots of little circular islands. Each of these little circular islands is also made of glass particles, but much, much smaller, so it has a much, much lower permeability. All right? And I must tell you, I don't remember how the porosity was altered from one to the other. I've forgotten about it. I'm not sure that there was much. They may have tried to keep it not. I don't know how much that changed, so I can't say for sure. I don't remember. But distinctly, the permeability was lower by a factor here of almost 100. And you can see here, it's rather dramatic. You can see these. Here's a single one of these particles here. And as time progresses, it starts out clear, and you can see that the fluid's the concentration's being swept out of it in a rather interesting way here. And you'll notice that the higher concentration is drifting off to the left. That's the direction of the flow. So the outside flow field is slightly affecting the transport inside the individual particle. Not much, but there is some effect there. Okay, this is a case of, I'm calling intermediate contrast. I'm sorry, this is a high contrast case. I've got these in the wrong order here. That's a low contrast and high contrast. So this was the extreme case here with the high contrast case. And then the intermediate contrast case, which is below these. A couple things are, well, anyway, some things are similar, some things are not. First of all, you have to check the timing on this. Whereas what's most interesting over here, at least to us, was the fact that the advection effects on the particles were much more pronounced than they were in the high contrast case. In the high contrast case, the ratio of those things was like about 3,000. In the intermediate one, it's about 100, and down here it was about 6. So we're basically changing by a digit as we go from low to intermediate to high. This is low contrast, intermediate, and high contrast. Now, I arranged them in this order for the following reason. If you want to do an upscaling argument to build a model for the low contrast case, classical homogenization theory, which we've been hearing about all along, gives you a very good model. It'll give you a uniform, well, it'll give you a number for your permeability, and if you use that one number in that parabolic equation and solve that one, you get really, really, really close to the answer. It's a good model. So the classical homogenization gives you a very, very good model for that situation there, for the low contrast case. It basically averages things out. It tells you what you would see if you looked at that process from across the street. Okay? For the high contrast case, and this one, the ratio here is about 3,000. An excellent model for that one was developed called the dual porosity model, or the double porosity model, by Douglas and Arbogast, and Hornung was involved in developing the model about 1990. In this one, you take one of those little islands and you look at its size, epsilon. The magic epsilon is appearing here again. Okay, but this time you assume that the permeability of that little island is scaled like epsilon squared. And the reason it's epsilon squared is because 3 equals 2 plus 1. Namely, you're taking an average, a volume average, of an integral of the amount of flux coming across that wall, which is flowing back into the field. That little island is acting like a source or a sink. And you do a flux calculation, and you find out that to balance the flux, to keep the flux nearly constant, as you shrink the piece and simultaneously shrink the permeability, the flux will stay constant nearly constant if you scale the permeability by epsilon squared. And epsilon squared comes up in lots of these examples. In the original Stokes upscaling, which we saw yesterday from Gideon, he had a 1 over epsilon in one place and an epsilon in the other place. They're off by epsilon squared for the same reason. But you have to sit back and look at the thing and just look at one of those pores and compute the flux coming across that to see how it's affecting its neighbors. And you find out that exactly the epsilon squared gives you that balance. So if you were tuning it with a microscope, no matter which level you were looking at it, you would always see the same amount of flux coming out of that island. Okay. Now, the classical homogenization gives us a very good model for the low contrast case. The epsilon squared model, the dual porosity model, is excellent at reproducing this situation. But it's a different kind of model, and I'm going to tell you what that is. It's premature. But that's good. I like impatience. Right. So the dual porosity model gives us that one. Okay? It's a more complicated model because it involves a system. But the system is very, very parallelized. Okay? So for computational reasons, it's excellent. That's why Arbogast and Douglas were interested in it. That's why they constructed it. Because it's a more complicated, but computationally speaking, it wasn't much of a price to pay for all of the good things that you get out of it. This was a hard thing to copy. By the way, classically, back about 60 plus or minus 10 years, Barenblad and company in Russia had devised ways to model these long-term tailing effects, and the way they did it was sort of what I call a parallel flow model. They had one parabolic equation with constants in it for the fissure system and another parallel equation, all of them distributed over volume. Another equation with different constants in it to do the fast. So one is doing fast, the other is doing slow, and then they linearly couple them together. A first order kinetic model. They just put differences between the pressures. A multiple of that is how much is flowing from one of these fields to the other fields, and that was the model that they used for it. Okay? I knew all about those because they were sort of background for some stuff I was interested in at the time, so I spent a bit of time studying those. I read his description of how he came up with that model, English version of it, of course. This was 1960. Anyway, it was, I read it many, many times, and in the process of reading it, I had just written down ad hoc, for no mathematical reason, but just ad hoc. From his descriptions, I wrote down models which are very, very close to the Douglas-Arbogast model. We called them microstructure models and proved theorems about them, okay? It didn't just because they were sort of mathematically interesting. But that's kind of how I got into this whole business. Now, we have an excellent model for this one. I'm going to show you how excellent it is. I'll have an excellent model for that one. I'll show you how excellent that is. And in fact, this group here, when they built this experimental setup, what they wanted to do was find a model which reproduced all of this. They didn't want it to depend on scales. Okay? This guy reproduced exactly the low contrast. Sorry, the low contrast case was reproduced by one model, high contrast by the other, and for the intermediate cases, nothing would get it. That's why we stepped into it. Because we know how to do this case, we know how this do case. Surely we can figure out how to interpolate between these, right? There's got to be some obvious way to do this. So the challenge here was to get these guys here. Let me look a little more here at the detail here. Just so you see, just to make sure we see what's happening. Here's a low contrast case. I'll give it in the right order this time. There's a low contrast case. Classical homogenization duplicates that perfectly. No problem. There's the intermediate contrast. That has certain characteristics, and the easiest way to describe those, look at the breakthrough curves, because that's what hydrologists care about. They don't care about what's going on in the middle. All they care about is, if I put this in, what's going to come out over here? Okay. At that time, nothing would duplicate those. and in the high contrast case. I'm showing you the same pictures blown up a little bit without the subtitles. Those can be done quite well. Again, the information we had in this experiment, which you do not see in the breakthrough curves, is what's going on in those little cells, and the difference between these, you can see the effects of the advection on the individual cells here. It's moving a little bit to one side, so there's a favoritism there. There is a little bit of advection getting into the cells. Over here, there's even more. It's almost ineffective here. You can basically ignore what's happening here for advection. Here you can't ignore it. It becomes a significant part. And there's so little of it over here, you won't even see it. And in fact, you'll see it you just won't see it. It'll just sweep through there at the same thing. The cells don't look that much different from their neighbor. Okay. Now, let me look at the breakthrough curves. Because this was the challenge. Low contrast case, starting with the black one, that's easiest to follow. Remember, we start off with it's completely filled, fully concentrated. We put in the fresh fluid from one side. So the breakthrough curve has got to drop from 1 to 0 somehow. And if the permeabilities are not too far off by an order of not more than 10, the breakthrough curves just sort of drop down and tail off a bit. That's sort of the traditional thing we see. And that you can model with a single permeability, a single equation, okay, and you can pick the constant to match that up. Not surprising, the constant turns out to be the one that you compute by homogenization. Okay, whoop-de-doo, it all worked. High contrast case. The purple line, which is kind of easiest way to pick out that purple line, because there's a blue one which is confusing, is to go over here. It's the one farthest to the right. The high contrast case holds on to what's in the islands the longest, and that's why this curve lasted the longest over here. This is a tailing effect. And so what happens, and this was also, okay, so it comes along and it starts dropping off, and then it kind of levels off here. So again, nothing happens. When something starts happening, there's a fast drop off initially, and then it trails off like so. You kind of see two different rates involved, okay? Obviously related somehow to two different permeabilities, even though they're really off by a big scale factor. By the way, this is on a log scale here, so these are really, really long tails. And there's the other one, which is high but not quite as high, does pretty much the same thing, just drops off a little sooner. Now the intermediate contrast case, and by the way, Haggerty and Zinn and the others in that experiment, they were able to match these long curves, the high contrast curves and the low contrast curves. They could match those spot on with the models that they had, with the corresponding models, the different models.
Forgive me for asking, but I don't quite understand what's being plotted. What's the pore volume?
I'm sorry, ask again, please.
I don't understand what you're plotting.
What we're plotting. Okay. I'll turn around this way. Okay. So here's the tube. So it is fully concentration 1, full concentration 1, and I start running in at a fixed velocity. I put in a clear fluid, concentration 0. So if I'm at the other end, I'm watching what's coming out. For a while I see concentration 1, and then as this front gets close to that, it starts dropping off, depending on how much the fluid's been spreading. And the amount it's been spreading will depend on the ratios of those permeabilities. So at the end, it'll either drop off quickly if the permeabilities are close, or there'll be a long tailing effect if the...
It's a function of time.
It's a function of time.
Yeah.
I'm sorry. Right. By the pore volume, it's been displaced. By the displaced pore volume, which is happening at a fixed rate, so that's really a function of time.
So I have to think of the horizontal axis.
Okay. It's the amount of volume of fluid that's coming across there. Okay. Per time. It's measured in pore volumes per time. This is a measure of time across here.
You measure the volume of fluid that's come out the other end?
Yes. Yes. Well, it's scaled by that, which is also linear with time, because I'm putting in at a fixed rate all the way across that thing. Okay, so it's coming out at a fixed rate, so there's a fixed volume per unit time coming out.
And the concentration is the average concentration, is it?
Total, yes, the average or total, yes.
Coming out, yeah.
Right, right. So that's the total amount coming out. And what has not yet come out has been stored or delayed from coming out. Again, these are the curves that hydrologists love to look at. This is
No, sorry. Is it the plot, the concentration of the instantaneous concentration, or is it the question of how much has actually been moved out of the thing? Is it the integral of the concentration?
it's the integral of the concentration over the whole channel.
But not the integral over time.
No, not the integral over time. It's the instantaneous.
Instantaneous.
Yep. Right. And by the way, when they set up the experiment, what made it all work was that they had these fancy ways that they could, because they were using glass particles in here, they could, take fancy pictures from here with their backdrop of light. And they could actually use the colors to measure concentrations of things. They could identify those. So it was actually a very, very cleverly constructed and well-controlled experiment. The kind of information that you rarely get to see. And certainly not in such detail. Imagine how much easier your life would be if you could really go down there and look what's happening down below. Not that you'd want to go down there, but maybe send something down to do it. Okay, so anyway, so the bottom line was these intermediate things, no model would match. Okay, so here's the issue. It's one I want to say that we want to study this problem. We want to construct a model which does not depend on the choice of scale. If we knew the scale beforehand, that's more information we probably know. We would like to do it without that. Standard. This is just repeating here, but basically we have good model at one end, good model at the other end, but we can't take care of what's happening. And what we want to do is to find a single model which represents the whole spectrum of scales simultaneously. Okay? The other thing was we also wanted the model to pick up the effects of advection. So I didn't put this in the slide, and we didn't really think about that until afterward, till we saw how much there was going on. We also wanted to get a description of the advection that was going on within the model. All right, I'm going to skip that one. The true model, the exact model that we've got here, is basically to solve that equation for the concentration. In fact, at this point, I'm going to ignore I'm going to ignore the advection for the moment. We really did it in the project, but I don't want to carry that along and talk about it right now. But I want to look just at the single parabolic equation describing that transport of the concentration, or just the concentration diffusing through there. I want to talk about just that equation and how we would upscale that guy. In the exact model, and obviously I've suppressed a lot of things here, but the point is I've got a coefficient here which has one value in the slow region, a different value in the fast region. And in the true model, since it takes on those two values, what I really want to do is solve an interface problem. I want to solve that equation with one constant on each of those islands, and solve that equation with a different constant on the surrounding flow fields, and want to couple them together across the interfaces by matching the value of concentration and the value of flux. So it's really a complicated interface problem, and because of that, numerically, it's difficult. It's really very difficult because we have so many of those little islands, so much matching to do, and so on. So numerically, this is a difficult problem. Formally, it looks like this, where that D is just switching from one value to another, but in fact, it's really those equations coupled with concentrations and fluxes balanced across each of those minute interfaces, and there are many of these. Okay, I think I've basically said just that. Right. And by the way, the coupling there is both through the concentration and through the gradients. It's a point that's worth mentioning here because I'll refer back to that later. Okay. Classical homogenization, the low contrast case. This was the part we've seen for days now. A quick cartoon of what we've seen. The exact model at micro scale, so there's a unit cell. I've written them down periodically here because it was easier to write that down, and our numerical experiments later were done with such a figure. But periodicity, by the way, has nothing to do with it here. In a low contrast case, we can replace that by a medium with a single permeability, okay? And the results are very, very close. The solutions are very, very close to each other. How's that constructed? You have to go into the unit cell. There's a copy of the unit cell. On the unit cell, you solve a corresponding flow problem, a Darcy-type problem, for which the input to it depends on a unit vector, a unit pressure gradient from one side to the other, but you have to do it, so EJ is a unit vector in the jth direction, so you first have a unit pressure drop across this way, you compute to omega 1, you have a unit pressure drop this way, you compute to omega 2, use those two omegas, you stick them into this fancy formula we had, and that gives you your that contributes to the value of that homogenized coefficient. But in order to compute that coefficient, you have to solve this cell problem. And by the way, the cell problem here, I just say again, depends mostly on the gradient of the surrounding quantity. Then use a linearity argument to plug it in and go through all of the other gymnastics and end up with that formula for the homogenized coefficient. So, in a nutshell, I've tried to summarize 4 lectures in this one period, in this one picture, but you know, that's not a good summary. But that model works very well for the low contrast case.
Right. So the groundwater flow people did a comparison with their experiments and the homogenization model.
Yes.
When they did it, I mean, how much detail did they put into their cell geometry to solve the cell problem?
How much detail?
I mean, did they just sort of measure? Okay.
Well, they knew it they were matching it with their experiment,
Yeah.
so they knew what their values were.
Oh, okay.
Okay, because they constructed them. All right. So they knew everything about the geometry, which is we always tend to forget about, but the geometry is what drives everything here. It's not just the values, but the geometry and the values of those coefficients. So they knew exactly what theirs were, so they knew what it should be, and sure enough, that's what worked.
But did they solve the real cell problems with those values?
Yes, they did. I'm wrong. Because later on we had discussions with them about that, and they sampled a few values and they did experiments to find out. They did some coefficient matching, find a single coefficient that matches those, and there was a coefficient which matched it, and it turned out that was, of course, the right one. Okay, so basically they were doing it as a coefficient matching exercise against known models in the low and the high contrast case. Now, special case of this, those blue islands, if it's not just a lower permeability, you can actually go to the extreme case of making it zero permeability. This is the obstacle problem. In other words, instead of having two different permeable regions here, one of those permeable regions is impermeable. So we call that the obstacle problem. It represents a case which turned out to play a role, and I want to keep track of this with a little bookkeeping. I'm not going to give a chalk talk, but just use this to keep track of things. In our in all the cases, we had our island here. This was the low contrast case, but there were comparable permeabilities in here. And at the other extreme, we have that same island, but instead make the permeability 0. Right. So this is a pure obstacle problem.
Are you also going to make the diffusivity 0?
Again, please?
Are you going to make the diffusivity 0 also? D.
Permeability here is 0.
Yeah.
So there's no diffusion. There's nothing happens here. Nothing gets in.
The diffusivity is also 0.
Yes. Right.
Those are two different.
Yes, I realize that. Right. But for simplification, I'm just talking about I said permeabilities. Okay. Right.
The dispersion
I
coefficient.
meant diffusion
You
dispersion
mean by-
coefficient.
by
I mean the
sound.
D. The D, right. The diffusion dispersion coefficient.
You also mean the advection is 0 and diffusive 0.
Right. The highest order term there has coefficient 0 in it. It's just gone. Okay. So nothing gets in there. The flow is only around that. So it's an obstacle to the rest of the flow. Okay. And this was a slight difference in small contrast case here. So most of it's flowing around here, but a substantial amount's flowing across there. All right. I'm denoting that with a 0 as a superscript on the solution and on the corresponding coefficients. I have a formula which gives me the homogenized coefficient coming from two different values in the low contrast case. And if one of those coefficients is 0, I just use that in all of my calculations, and that gives me another number, which of course is smaller. Okay? That's sort of the smallest or a lower bound. But anyway, that represents the obstacle problem. It turns out that particular problem is going to play a special role here, which I should have observed long before we did this thing, but I did not until we were working on it did I realize this. Okay? A remark about the high contrast versus low contrast cases. When you do the homogenization in the low contrast case where your ratio, your permeabilities is about the same, you get estimates on your solution like that. You have uniform bounds on the solution and on the gradients. So you're bounding the values of your solutions, and you're also bounding their gradients. You get variations like so. In the high contrast case, because that epsilon squared in front of the gradient terms, it's actually the gradient squared when you write the variational form of the equations, those derivatives can grow like order 1 over epsilon. And you get waves, variations that look more like this. The values don't get any bigger, but they jump much more quickly. The gradients are larger. And by the way, the gradients play an important role. The gradients are actually more important than the values themselves. Okay? You don't care about the pressure, you care about the velocity. You want to know what's happening here. Okay? I keep referring back to the flow problem when I really mean the transport problem here, but anyway, it's we don't care as much about the concentrations as we do the fluxes. Well, at least we should. Okay. So these little waves have different shapes here. But the important thing here is there's a difference in the way the gradients are controlled between those two different cases. Now, to follow up on that remark, you might think that if I put epsilon squared to scale 1 for the high contrast and epsilon to the 0 to get the low contrast, maybe epsilon some other power is going to work to give me the intermediate ones. Doesn't work, because you don't get this cascading between the different scales. There's also this scale difference, and you can't match them up. You just have a total mismatch, and nothing works. Okay? It looks like an easy solution, but it leads nowhere. Okay, here's the microstructure model, the dual porosity model. And I've written it in discrete forms as if we had discrete islands here. This emphasizes it has nothing to do with periodicity. Okay? If I had just the obstacle problem alone, the concentration would be described by this term and only those. So if I have this term and this term, those two guys there, that's exactly the equation that describes the solution to the obstacle problem. So what's new here? Well, each of those islands acts as a source or a sink because they're two-way coupled to the global flow. Let's look at them globally. On each of the islands, the little omega, these little omega tildes here, and I have one for each I. On each of those, I solve for its corresponding concentration. And what do I use for interface conditions? The interface condition, I solve this equation here subject to this Dirichlet condition. The value of the concentration on the boundary is equal to this number here. It's not a function, it's a number. It's a very special function. Okay? I look at the surrounding medium. I average the concentration around that very small island. I take that number, which is changing with time. That's the outside concentration. I take the average of that and and take that average value and use that for my input to this local problem. Okay? So the cell responds to its neighbor's concentration. Solve that cell problem, get the concentration, and once you've got the concentration, now compute the flux going across the boundary of that region, weighted appropriately, and the flux coming across there becomes another source or sink for the global equation. That's the coupling. That's the physics of the coupling in there. Again, the global flow field is defined everywhere in space. It's sort of been smeared out over the whole region. You go into any point where there's an island. At that island, you average the concentration in that region. Use that as input to the cell problem on the boundary only. Solve that parabolic problem. You get the concentration inside. Now compute the flux coming across its boundary, and that becomes the source or sink for the global equation. That's your two-way coupling. Notice it's Dirichlet data going into the problem, Neumann data coming out. Values going in, flux coming out.
Can that be can the second equation be treated quasi-statically?
This one?
Yeah.
It's the opposite direction you don't want to, because that's a slow one.
Okay.
What has happened to the advection term?
I'm ignoring it. I'm not carrying the calculations. It's all there. I can do it with advection. In principle, nothing changes, but I'm ignoring it for this presentation because I just don't want to have too many things that complicate the picture. I've got enough terms to fill up my slide already. It's a theatrical device. Okay, so the problem, the full problem in our
how can the concentration at the output change?
So
if you've ignored the advection?
I'm describing here. So I'm concentrating on the PDE that describes the problem, and I'm sort of suppressing the advection in that thing. So you can think of it as a diffusion problem. Think of it just purely a diffusion problem. It's already worthwhile there, but it's not exactly the application I wanted. But the same sorts of things happen. You have high concentrations, low concentrations. The concentration moves across the thing, but it's not advected. It's just moving by diffusion. But the same sorts of things will happen, but at a much slower rate, of course. The real action happened with the advection, which is what really makes it much more interesting. But again, for this presentation, I'm ignoring it. In the paper, in the write-up, you'll see all the terms are there. It's just more to be followed. Okay? So this is the upscaled model. And I've written it in a discrete form, and I'll show you later the continuous form, which really doesn't change in spirit at all. And this is a schematic of that double porosity model. In that double porosity model, you basically have two things going on. There's your exact model, and you replace it with the solution of an obstacle problem, but it's coupled. At each point within there, you have a corresponding cell problem. So you have to have a family of these cell problems, like this, one associated with each of those islands inside there. and that's your system. So the problem has a different flavor altogether. This is a consequence of that epsilon squared scaling. Okay. Now, let me try to write what we have in a slightly abstract, maybe too efficient way. What went into the local cell problem was the following. If I look at this quantity here that I computed where I was taking the average of C, it's an averaging operator, so I'm averaging my flow. This is what I use for my input to the cell problem. What came out of it was my flux calculation, which I'm denoting by something acting on this quantity here, and that something is this operator here. So think of this as the operator of averaging, and this guy here is the operator of computing the integral of this guy over the boundary. Those two, if I set things up in the right function spaces and the right scalar products, okay, these operators are dual to each other. So I have an operator going in and an operator coming out. I have the operator going in and I have its dual coming out. So in the right L2 sort of setup, these guys happen to be adjoint to each other. And my cell problem looks like this guy with the operator itself giving me my input on the boundary. So I take this guy on the boundary, and that gives me my cell problem, and then I take the output of my cell problem, and I compute the corresponding adjoint operator acting at the point, and that gives me my output at that point. So I've got it set up as an operator, solve the problem, and the adjoint operator coming back out. That's the construction of the problem. And we know, by the way, that sort of a construction preserves self-adjointness. If the intermediate operator were self-adjoint, then putting an operator in, doing the self-adjoint, and then following it that way gives me another self-adjoint operator. So what that really means is this is somehow related to energy conservation, and we can do that directly. But I've really said this already, so that's really what I was just describing. By the way, interesting calculation here. That flux calculation I did, since we're talking about the solution of that cell problem, that parabolic equation, I can relate that flux going out to the integral of the time rate of change of the solution. So that's d by dt of this guy here, but that's the quantity of the concentrate that's stored in that cell. So that gives me a term which is d by dt of a storage term. So each of those cells is giving me a secondary storage at the corresponding point. And that storage term has a delay associated with it, dependent on its local diffusivity, okay, which gave me these delayed storage effects. So I can see all the pieces to this guy in these various terms. Okay, so here is the way we went after this. The high contrast case is described where we put in a constant values. We sample the concentration around the island, okay? And we take the average value of the concentration, use that for input, solve the cell problem, and then take something out as a consequence, okay? So here was the idea. Instead of approximating that concentration with its mean value, do a better approximation. How about an affine approximation? That way we can include the gradient effects. That's what's missing, because in the low contrast case, it was the gradients that coupled the cells. That's what we gave up when we went to the dual porosity. So somehow we've got to include both values and gradients into the cell to get the full effect, if we're going to catch it at both extremes, okay? And then we have to worry about what's going to come out. Okay, so if we're going to get the gradient effects, how do we choose one? Suppose I have something like this and I want to use a linear approximation of this guy. So this is a calculus exercise here. If I want to approximate this guy, do I use Taylor? Probably not. This is a typical profile I would see. If I use a Taylor expansion, I get 0. Okay, I missed everything. Forget that. Let's do an L2 projection. If we do an L2 projection of this red curve, I get a slope kind of like that. Good, but I can do better actually. Okay, and the better thing I do is the following. And this is really motivated by the spaces that we're working in, spaces of gradients of functions. Average the gradient over that region. So this is what I'm calling the H1 projection, not the L2 projection, but the H1 projection. I take this function here, I compute its gradient, and I average the gradient. If I average the gradient, that's not going to last forever.
That one has a laser pointer too.
Okay, it's working now. Just doesn't want to turn off. If I average the gradient, I get this blue line, which gives me a better fit.
Well, is the goal in the fitting, is it really to get things right at the endpoints?
Over the whole thing, to try to get something which is a stronger.
I guess my question then is why?
Yeah, why that one?
Well, why is white blue better than purple?
Why is blue better than purple? I've forgotten now, but you can come up with some examples where it looks like it's better. We were trying it on different waves, different shapes that we would see and expect to see in there. And this is the one that seemed to do the job better. And I don't know why. I'm sure there's some good approximation theory reason why this worked better. But this is the one that came out of it. And the other thing is when we do, because of the variational formulations of the problems, this one kind of comes up naturally also there. Turns out to be most easily fitted to the modeling process. Okay, so we decided on this way of doing it. The important thing is we have a way of constructing an approximation for the gradient, which is actually working well. So basically, I average the function, that goes in a constant term, and I average its gradient, that becomes the affine part over here. And this is the centroid of that region, so there's something here averages out to zero. So that guy averages out to zero. So they don't interact with each other. Okay, so I have the constant plus a linear part to give me a tighter fit to the matching. That's what I now use as boundary data on the cells. Now, I'm going to flip through it again because I don't want to take more time with this. I've already used up too much. What comes out? What comes out is the dual of that operator. You compute the dual of that operator and you get it in two parts. The first part, which is dual to this guy, is the same thing I had before, okay? Which you just integrate the flux average the flux over that boundary, okay? And for the second part, you get this factor here, which means you're computing the first moment of the flux around the boundary. And that first moment is basically saying if your flux is strong on this side of the cell and weak coming out that side, then you took the first moment in this direction here, okay? Then you're picking up the overall effect as when it's just sort of pushing fluid this way. So with that cell, you have associated not only the flux coming out, but also a flux field, whose divergence now becomes your secondary flux. I'm sorry, that becomes your secondary flux, and its divergence is yet another term in the equation. So what we end up with, this is just saying again what I've already said, and this was the calculations. I'll just point out to them as we go racing past here. The dual of the first part of the guy was the average over the part, okay? There was its dual, and the dual of the second guy, the first moment was this guy in here. But basically this slide here is just this boring but necessary calculation of the duals of the operators so we know it has to go back into the big equation. Right, and that was a summary of it all. Get the mean value of Q and plus another part which involved the first moment. Okay, so we end up with this model. What do we have this time? Again, there's a solution to the obstacle problem. This is the equation associated with the obstacle problem, as if the islands were just, nothing was coming in or going out. Okay? And so this is the effect of the obstacle. This is the effect of those islands. What goes into them is the average value of the concentration plus, sorry, that's the wrong one. Average value of the concentration plus the first moment of the flux. That's the input to the cell problem. What comes out, the dual, is going to be the average, or the total flux, effectively an average, the total flux coming out, and then there's another part This term comes up integrated against the gradient, so we're really looking at minus the divergence of this guy here, which is a characteristic function of that little island. It's 1 exactly on the island and 0 elsewhere. And this is the quantity here, which is that first moment of the flux. So that's explicitly what the model consists of. And this is a new term that goes into this intermediate case. And in fact, this is a model that we can use over that full spectrum. And here's the punchline. Using this model and this one model only, and this is numerical calculations, so these are calculations. At the low contrast regions, these red lines, that's these guys here. Those curves match up very close, and certainly the same shape and very close in values to the experimental values. We can choose numbers to match them up. Okay, so the low contrast case is covered right there. The high contrast case, these guys, in particular the black one, same as before, it drops down quickly and then tails off. There's a little bit, there's actually looks like a third slight variation slope over there, which we didn't see in the experiments, but okay. This is matching up very, very closely with the high contrast case. It's reproducing those. And in addition to that, all these intermediate cases here, we compute those successively as I go from yellow to turquoise to blue to green. You can see I'm getting these guys here. Look what happens. It drops off. There's a flat, it'll drop off. There will be a kind of a certain slope here. Then there'll be a third piece that drops off. Those are the things they were seeing in the experiments, what none of the other models would pick up. This guy's picking up exactly, and you can actually quantify them and see the transitions as you go from low to high contrast case. The whole spectrum is there. There's no scale separation in this model. It's just there to represent everything, the two extreme points and everything in between. And this picks it up. The continuum version of this model, the one that comes up in the theory, which I'm not about to describe, and this is a full, you can see the velocities here. I finally put back the full problem so we can see the whole thing I was refusing to carry along as we went. You see that the fluid velocities are involved in all the calculations still. They're part of the flux, of course. So basically you put those terms in here where the flux has to be added back in there. So if you knew the velocity, here's the problem from here down. There's the global field and the Q. The Q is the same thing we computed before on each island, except now it's computed at a generic island sitting at each point in space. So for each point in space, I have associated with it a microcell. So geometrically, you can think of this as your whole global region, and at each point in space, I have associated with it what you'd see if you zeroed in with a microscope at that point. There's what you would see. There's what's going on. There's the connections with it. There's the effect of that little microcell sitting at that point. It's a source or sink term for the equation, and that new term there consists of two pieces. One part is the delayed storage term. Okay, I average the flux coming out, a concentration flux, and a second part which is a divergence of this delayed flux term. So I have a storage term and a flux term both in it. The whole thing is there. That was it. And the part we're not going to talk about is, what if I go through the calculus exercise of representing each of those, that Q and Q star combination? Try to write that, just write out a formula for it. You can do that. If you have simple geometry like circles, you can write down formulas for solutions by separating variables, go through horrendous calculations, 3 weeks of calculus, okay? And you can actually write down the convolution kernels that come out of all this, and you can write that whole sucker as a single functional equation with all the terms involved in there. So the good news is you can go through it. The bad news is don't waste your time. You get so many terms in there that to numerically resolve that equation, think of the memory with these slow tailings going on, going into those convolution terms. Computationally, it's unapproachable. It's not only difficult, it's just unapproachable. You don't even want to think about doing it. I'll stop here. Thank you.
So we're running a little late, but do we have maybe a quick question or two? Hey, I'll just ask, say, remind me a little bit of sort of Maury-Zwanzig formalism.
I don't know that.
Oh, okay, it's where it's a splitting into fast and slow variables. And then you end up with a memory term that then comes back into the other one.
Certainly formally sounds like it, yeah.
All right, let's thank Ralph again.